Namaskar my dear friends. Let us talk about one PFC controller IC which is there from we are taking from ROM semiconductor. So our main aim is to understand how PFC controller IC works and how it can be like very helpful to us in our PFC correction, that is power factor corrections. Okay. So we'll talk about how to design and details of this particular PFC application, which is the IC that we are taking is BD7695FJ. Okay. It can be utilized in our lot of application like LED lighting equipment, basically nothing but LED drivers or something like that. We have AC adapters, like we have some chargers or something like that. Let us say we have laptop charger or some other kind of chargers. We have TV, refrigerators, fridges, so many, like our washing machines or all those things are there. So generally how power factor correction works is basically it is going to reduce your like consumption, or like it can be very helpful to your have requirement for power factor correction that is guided by the lot of agencies. Okay. So let's open datasheet and try to understand different features that is there already with this particular PFC correction IC. So as we have, you can see we have two versions, which is one is BD7695 series and one is BD7696 series. Okay, we'll see what are those two things. One is having brownout and one is not having brownout, so that's the only change that is there. Okay. If you talk about this particular power factor correction IC, so this can be utilized in your AC/DC supplies, which is suitable for all products, okay, needing power factor improvements. And this power factor adopts actually boundary condition mode, boundary conduction mode, and also it is going to reduce your switching losses and noise. Okay, so what is the thing that it is going to do? My power factor correction IC is going to adopt a condition of boundary conduction mode, as well as it is going to reduce my switching loss as well as noise reductions. Okay, and this, how does it do that? So this does all these things by applying a technique of zero cross detection, that is ZCD. It also incorporates some of the like total harmonic distortion circuits. Okay, so it can reduce your THD, that is total harmonic distortion circuit, and it supports actually class C of IEC 61000 3-2. Some of the basic features that is there with this particular PFC correction ICs, PFC controller ICs, basically it is having boundary conduction mode PFC, very low total harmonic distortions, it has low power consumption, it is having VCC under voltage lockout function, that is the supply input voltage lockout function. So let us say your IC is supposed to work from 10 volt to let us say 24 volt, then it will not work below 10 volt, that is under voltage lockout. It is having ZCD by auxiliary winding, so we will have auxiliary winding, and this is how it will be working with zero cross detection. It has a static over voltage protection by VS pin, that is your one supply pin, one feedback pin is there. So feedback pin is actually here VS pin, and this feedback pin will be supporting for over voltage protection. It has error amplifier input for short circuit protection. So suppose you have very like very high current at the output, at that time you will be having error amplifier to shut it down. It has a stable MOSFET gate driver, and it has a very good soft start as well. As you can see, very key specifications, so we have a VCC range that can work from 32 volt 12 volt to 38 volt, right? And it has operating current of 60 just 0.6 milliamperes. Okay, it's not even taking 1 milliampere, and the operating temperature range you can take it into account as minus 40 degrees centigrade to 105 degrees centigrade. Okay, so why don't we do first like pin configuration, then it will be easy for us to understand complete circuitry. Okay, so how does it work and all those things we'll see one by one. So this is my PFC IC that is looking like, which we are going to talk about. So it has 8 pins. You can see we have VS pin, EO pin, multiplier pin, and this is current source, like a current sense pin. We have ZCD pin, that is zero cross detection pin. We have ground pin. We have output pin, which is going to get connected to the output of our like a gate. I mean it is going to drive the gate of the MOSFET, and this is the supply pin. Okay, so as I already told you, VS is your feedback pin, which is a input pin. EO is your error amplifier output pin, which is going to give you the lot of like a faulty or something condition. Those can be taken into account at this point. We have multiplier input pin, we have overcurrent detection pin, we have ZCD, that is zero cross detection pin, we have ground pin, we have output which is going to external MOSFET driver pin, and this is power supply pin. Okay, a very simple technique of working with this PFC controller IC is this. So let us say, how does it do this PFC, or how does it do this power factor correction? So let us say we have AC input which is going to be let's say 90 volt AC to, let's say 90 volt AC to 265 volt AC. Okay, so this can be all these things. We can put all like here let us say safety, like fuse, MOVs and all those things. We can have a lot of noise reduction devices, let's say CMC or all those filters and all. Then we can send it to our bridge rectifier, which is going to rectify the output voltage. So this is rectified output voltage here at this particular point. Okay, it will be taking a resistor divider, and this is how you will be supplying the voltage to multiplier pin. Okay, so this is our IC that we are talking about. This is 8 pin IC. So this multiplier pin will be taking the voltage divided input. Okay, and this is ZCD, which is going to connect this to this particular CMC, you can see. Okay, that is common mode choke, something like that it is there. So one of the line will be connected to this ZCD, which will be deciding when the output has to go out or not, right? And based on this, it will be switching on, switching off this particular MOSFET. Okay, so this particular MOSFET driving will be done by this ZCD detection. If you talk about this output, then you will be having PFC corrected output, and this is how, let us say we are going to have 400 volt here, and then you can send it to your like a primary of your flyback converter or something like that. So lot of like applications are there. So you can send it to your flyback converters, or like any power supply devices or adapters where you want to design a power supply device. So this will be the input of your primary side, which is going to be having a power factor correction. One more advantage is, this is the output voltage, let us say 400 volts. It can go ahead with voltage division, and then it can go ahead with feedback pin. So this is my feedback pin, and at the same time it is going to go to error amplifier pin also, which will be giving an error or something like that if it is there. It has a current source pin, current sense pin. So this current sense pin actually indicates how much current is flowing through the let us say this is my drain, this is my source of the MOSFET. So what is the current that is flowing through this? Okay, so your aim must be to save this particular MOSFET also. It should not go over current. Okay, so over current protection will be done by this CS pin. And similar to that, one VCC pin is there, which will be taking the input supply voltage for this particular IC. That will be done through one like resistor divider and let us say one clamp diode, and that will be decided. Alright, so we have understood a basic understanding of our pin configuration and the power factor correction process that it will be doing. Now we will go in detail through the data sheet, so that you can extend the same concept either to this particular IC or to any other power factor correction IC that you are taking from your design point of view. Okay, so this is just one example that I am going to give you. So let us say talking about this typical application. So this we will come a little later, because we want to understand this particular IC like details and definitions and all those things. So we'll see this particular typical application at little later stage. Okay, so we have seen this pin description, like what are the pins and how these pins are going to have their own functionalities. Let's talk about block diagram. That is very, very important. Okay, so in this block diagram as you can see, we have VCC pin. Okay, so this VCC pin is going to have it is having one Zener diode here, which is going to clamp this input voltage if there is some very high voltage or something. So this resistor will be there of very high value, which will be supplying this particular supply voltage. Okay, so this is VCC, and this is my kind of RCD snubber or something, so that can be taken into account at the input of this. And this is my ZCD pin, which is zero cross detection, which is connected to the one pin of the it can be told as a transformer. Okay. As I told you already in the beginning itself, we have the SE source, we have fuse protection, then MOV. I mean, MOVs also you can put if you want. Okay, that is also always recommended. Okay, so that is there, and then we have all these X capacitors and then filters. Filters is nothing but CMC chokes or something like that. That is common mode choke. Then we have X capacitor. X capacitor is here also. No, this is not X capacitor. This is bridge after rectified voltage. This is the bulk capacitor that you can consider. We can also have some other capacitor that we'll see in detail, like how to design this particular phase. So we have already lot of circuits earlier for our power supply device. So in that case, same way you can design this particular circuit having all the fuse or filter circuits or MOVs or TVS diodes and all those things. Okay, so that's I'm not going to discuss right now. Coming back to this multiplier voltage, so there will be one resistor divider, and this resistor divider will be giving me a multiplier output that will get connected to the multiplier pin. Okay, now coming back to this VCC pin, we already saw. Let's talk about this VS pin. So VS pin is nothing but the feedback pin. So feedback pin will be coming from this output. So you can see here output pin is there. So this is what going to go to the primary of our power supply converter. That is my uh, let us say playback converter, or we have some primary of my transformers. Okay, so this VS pin will be deciding the voltage level at this point, and this is having a comparator here. So our aim is to make sure that, let us say this is, let's say 400 volt. So accordingly you have to decide these two resistor, let's say R1 and R2, and in that case it must be less than 2.5 volt. Okay, then only it will work. So if it is less than 2.5 volt, this will not get trigger out and error amplifier output will not come up. Okay, that's the main understanding. And similar to that, zero cross detection will be deciding the decision based on this. Whenever you have to have the output, this is the zero cross detection. So based on this VS pin, that is your feedback pin, it decides and it shut down if it is having short compensation or something like that. Our main aim is to understand this particular decision will be done, and it will be deciding about pre-driver circuit, and this is our push-pull MOSFET configuration. Okay, and this push-pull MOSFET configuration is going to drive to my external MOSFET. So let us say this is my N-channel MOSFET, which will be having high current capability, capacity, and here we will be having one R sense, and this R sense is going to sense the current flowing through this particular MOSFET whenever it is on, and at that point this can be taken into my CS pin, which will be deciding the short circuit protection about that. Alright, so this was all about this particular block diagram of this particular IC that is there. And as you can see, internally we have a VCC, and that is going to go to a regulator or something like that. We have a bridge, a 5 volt regulator, and this is going to get used for our internal circuitry. We have thermal shutdown as well, like this particular IC will shut down automatically once it reaches to a particular temperature more than, let's say, 105 degrees centigrade that it was mentioned. Okay, so as you can see, there is no need of any external controller supply or controller pin control. It is just going to work on its own everything. So you have to have an understanding of this PFC correction IC is capable of doing all the job that is required for your power factor correction. Let's move to the next point. We have already discussed about this particular power factor correction outline. Okay, so we are not going to see it again. Coming back to this point. Okay, so let us say switching operation timing chart. So I mean it is all about that same thing. Let me just give you an example. This is my output pin, which is going to have a gate driver. So at that gate driver, let us say it is going to high. So when it will go high, at that point the MOSFET VDS, that is voltage, let us say I just draw here voltage across the this is my drain, this is my source, this is my gate, and this is my out pin that is going to my gate. Okay, so this is the main understanding that we should have. Okay, so what is happening is, whenever my output will be high, then what will happen, this particular MOSFET will get switched on, let's say my Q1. Okay, and at that time my MOSFET VDS will go 0, so it is going low, and in that case you can see my actually inductor will start getting charged. So the current through the inductor will start like increasing slowly. Understood? So this is what is happening at that time. Voltage across CS, that is voltage across my current source, current sense resistor, this is my, let us say, R sense, and this is going to get connected to my CS pin. So as you can see, the voltage at this point will also start increasing because there is a current flowing through this particular resistor, because the current flowing through this drain to source. Okay, so you can see voltage across CS pin will start increasing slowly. Understood? And at that time voltage across ZCD point, that is zero cross detection, will be 0. Okay, so for next cycle it will again go into the next phase, and then again it will go back, then only it will start. Okay, so this is how it is going to work out. So you can see, if you want, you can read this particular understanding again. Okay, let's talk about gain amplifier. So what happens is, let us say we have PFC output that we are going to have, let us say 400 volt. So in that case what happens is, we want to like monitor this or regulate this particular voltage to 400 volt itself. At that time we will have R1 and R2, and this is going to set a voltage of, let us say 2.49 volt, or like something like that, let's say 2.5 volt. So whenever this particular voltage output voltage goes more than 2.5, it will again like shut it down, and then again it will shut it like restart. So this is how it is going to have a feedback functionality. So basically I have already told you regarding this feedback functionality in lot of switching regulators, where you will be setting a regulated output voltage. Let us say V out we want to set, and at that point we have set always, this is my VFB pin. So R1 and R2 will be designed in such a manner that this output voltage will be regulated to your specified voltage. So this is same way we have to do here, R1 and R2. Okay. Okay, and this you can see gain amplifier actually controls the EO voltage by this gap. Okay, so there will be a little bit hysteresis as well. It will not immediately switch on or switch off, something like that, and this is how it is going to regulate your PFC output. Coming back to VS short protection. So VS short protection, what is happening is, the VS pin, nothing but the feedback pin, just now we talked about this VS pin. Okay, this VS pin. So what is happening? Let us say PFC output is going to go low. So in that case it will be like lower than, let us say, 0.3 volt, which is typical voltage, which is less, like V short. So at that point my switching output is there. Okay, which is going to my gate of the MOSFET, that will switch off, that will stop switching after these many pulses, like after 3 pulses it will get switched off. So you can see we have 150 microsecond typical time or more, and then IC stops switching. So this is how it is going to save or going to protect for feedback short circuit protection. Okay, let's talk about over current protection. So sorry, over voltage protection. So over voltage protection also the same thing. Just now we talked about over VS protection, VS short circuit protection. So same way, let us say R1 and R2 are designed in such a fashion that this is 2.5 volt. Once this particular voltage goes above like 391 volt, or let us say 400 volt, so what will happen? This particular voltage, let us say Vx, so or Vs pin, will go higher than this internal V reference. So this internal V reference is 2.5 volt. Okay, V reference. So as soon as it goes higher than that, it will switch it off, let it will stop switching by protection function. So this is how you are going to save from your over voltage at the PFC output. Okay, coming back to other details, let's talk about ZCD pin. Okay, so how ZCD pin is working, that is zero cross detection pin is working. So you can see we have ZCD pin connected to the like transformer, one of the inductor, and another inductor is going to the output, which is going to give you PFC out. Okay, so this PFC out is actually like the current is starting, and like current is increasing to this particular inductor, and then it is going down, increasing down. Why? Because this MOSFET is getting switched on and switched off. So basically this output pulse will be in a pulse format. Okay, based on the ZCD detections. Okay, and this is how we have a zero cross detection pin working based on the output that you need here, and accordingly this my MOSFET will get switching. Okay, so basically my drain to source pin will get switching on, switching off based on the output that is coming from the control logic that is decided by ZCD pin. Okay. Coming back to next part, we have already seen this ZCD pin. Let's talk about multiplier. Okay, so there is one multiplier pin also, which is going to, like the on width of output pin is fixed by in multiplier output. Okay, so whatever the on time that is there, let us say we have one output pulse that will come up, right? Output pulse to drive the MOSFET. So that on time or on width, like what is the duty cycle that will be decided, that will be decided by this multiplier pin. Okay, so if you want to have this VCS can be expressed in the following formula. Okay, so in that case we can do like K times V multiplied into VEO minus 0.9 volt. Okay, so this is how we will be utilizing this particular formula to decide our like R1 and R2 at the multiplier phase. So basically at the input, like rectified output will be there here. So let us say R1 and R2 is this, and this will go to my multiplier pin. So we'll do that also during our circuit design as well, but however this is how it is going to work upon. Now let us talk about next one, which is going to be this is fine, this is we have already seen it. Okay, okay, multiplier pin. What is happening in multiplier pin? This particular output is there which is going to drive the gate output. So multiplier pin, how it works is, when the state that multiply pin voltage is lower than V brownout 1, okay, which is 0.8 volt. So this is 0.8 volt and continues for T brownout 160 millisecond typical. So it continues for that much time, all right, or more. The IC stops switching by brownout function only in this 7696 function. When multiply pin voltage becomes higher than brownout 2, which is 0.97, so let us say this is 0.97 volt, so let's say it has gone to 1 volt or something. Okay, so in that case what happens, the IC switches again. So as you can see, like this particular switching is happening based on this particular multiplier pin voltages. So whenever multiplier pin goes down, and as you can see it has gone down and then again it is going up, and it starts switching. So once it goes down, then it stops for that next cycle, and then it takes switching again, and this is how the output pin will be available. So this will be driving the gate pin. CS pin we have seen multiple times how to like have a current sensing, and this is how it will be giving us an understanding of R sense. What is the current that is flowing through this particular drain to source. So basically the current ICS or ISC, whatever short circuit current or something like that you can define, that current will be decided based on this particular overcurrent protection logic. Let's talk about other functionalities. What is the thing that is needed? Anyway, this we have already talked about. This particular IC should work from 12 volt to 38 volt, so we will stick to that point. Okay, we have talked enough about like absolute maximum ratings and all those things, so that you have to always take into account whenever you are going to design any ICs. So your rating must not exceed from this particular like maximum absolute rating that is like given in the data sheet. And make sure that this current which this is not the current that is going to decide about the gate, this current which is going to my drain to source current. So this is my R sense and this is my CS pin, so the current sense pin. So this is not the current that is defined here. This is some other current which is output peak current. So output peak current is this current which is going to drive the gate of the MOSFET. Okay, so just do not get confused about this current as this current that is flowing through the drain to source of the external MOSFET. I wanted to highlight that point. Now coming back to the copper like a PCB layout guidelines and all those things are there, this ones. Let's move to next one. If you want to have like ZCD block, what is the different voltage level, ZCD1, ZCD2, so all these are actually tabulated here in one table. We have same way protection circuit also. So when this VS pin, that is feedback pin, stops switching, so as you had seen 0.3 volt was there, it continues for 150 microsecond. So all those things we have already seen. Okay, next we will talk about directly circuit. So if you come down, yes, coming back to this example application circuit. So one of the example application circuit that is given here. So let's start with the discussion very quickly. We have AC input here. Let us say 85 volt AC to 265 volt AC generally is the range that we always take, and this is my line and neutral. So it has been like saved by a fuse. So fuse of proper current rating we will be always like deciding based on the output power that we need in our power supply. Okay, and this is the resistor that is going to mitigate or have the functionality of at the input between line to neutral. Okay, we always try to have some MOVs or something for transient suppression, so we can always put here one like MOVs at this particular point. Now we have like X capacitor and Y capacitor. So X capacitor will be always between line to neutral, and Y capacitor will always be between line to ground and neutral to ground. So this is how it works. And coming back to this CMC, that is common mode choke, then again we have X capacitor, and then we have bridge rectifier that will be actually rectifying the output to a DC signal. So from AC we are going to convert it to DC, and we will be having one bulk capacitor kind of thing here. And at the same time, this is my multiplier pin resistor divider. So this is resistor dividers is going to decide a voltage level which will go to the multiplier pin. Okay, then coming back to this VCC supply pin. So VCC supply pin is also, as you had seen already, that there was a Zener diode inside also. So you can just have one resistor and directly you can supply it to this particular point, and that Zener diode will take care of that. And this RCD snubber is actually going to like decide at the input. So this is my RCD. There is one more output pin. So this output pin is going to go here at this particular point, which is going to drive the gate of the MOSFET. So this is the external MOSFET that we are actually concerned about, which will be driven, and the output will be keep on coming based on the inductor charging and discharging. Okay, this particular output actually is regulated based on the voltage divider of these two resistors. This one resistor, I mean R17 and R18 actually series added, so this is one resistor only, and these two are parallelly added, so these are another resistor. So this is going to be my VS pin, which is my feedback pin actually. Okay, so this feedback voltage will be going to get connected to my VS pin of the IC, and this is how it is going to regulate the output voltage. If there is any over voltage or something like that, it will give an error to the error amplifier output, and this is how it will shut it down. This particular IC will be shut down. Okay, so this was all about this particular complete circuit that we had seen. There are a lot of snubber circuit that has been used, like this is one of the like RD snubber, and this is RCD snubbers. Okay, so they are going to like mitigate any ringing or something like that that is there in the circuit. So this is how a very simple circuit that was there from the example point of view. One more circuit is given. Let's just do that as well. If you want to design the output values or something like that, you can always use this particular formula. Okay, so what you can do is let us say V output, if you want to set it to 400 volt, okay, or 398 volt. Okay, so in that case you can have 1 plus, this is 1 will be like R1 and R2 only, because we don't want to have lot of calculation. So let us say this is my output pin, and this is my R1, this is my R2. Okay, and this is going to my VFB pin. Okay, which is actually nothing but VS pin here. So basically this R1 and R2 will be decided based on this particular formula, and we have V amplifier is nothing but 2.5 volt. Okay, so 2.5 volt you have to take up, and accordingly here 2.5 volt is given. So you decide one of the resistor, let us say 10 kilo ohm, so another resistor will be calculated based on this particular V out that you want it. Okay, and accordingly you can put that value, so that R upper and R lower you can say, or R upper and R bottom you can say. That is how it is going to work. Calculation of inductance. So generally for output power of 200 watt and output voltage of 400 volt, inductor of 250 microhenry is actually like a suitable value that they are saying. External part for VCC is nothing but like 122 microfarad or more capacitor is needed at that particular point. So basically VCC supply pin was there, so there you need to have one let's say 47 microfarad with 50 volt rating or something like that we should always put, so that it is better. Okay. Okay, so attention to the board design. If you want to have a proper board designing, then how to place the components, and like that you have to talk about this particular three capacitors, okay, that you are going to utilize in your multiplier pin, one capacitor and one capacitor near the like a VCC pin. So this VCC pin capacitor C8 and C9 must be very close to the VCC pin IC, and this C7 also should be very close to the multiplier pin. Okay, so this is how one recommendation is there for our board designing. Coming back to C14, that is one capacitor between ZCD pin and the ground, basically is going to get connected very closer to the ZCD pin, otherwise it will be like not giving you proper result or very efficient result. Similar to that, there will be one like this is nothing but current sense resistor, like RCS, let us say. So this is one RC that has been used. Okay, so RC filter is going to give you the filtered output to the CS pin, that is current sense pin. So you have to make sure this particular current sense like a filter capacitor, that is C13, must be closer to this CS pin. Okay, so this is the board output pin that is there. So what they are saying is you must locate this part which is like inside the dot line near the IC. So that's the main understanding that I already told you. Okay. And as you can see, one more thing in addition, it is necessary to part placement to avoid the interference with switching lines and high current lines such as inductor and drain. So basically this is the inductor that is there with us, and this is the switching line, that is drain of the MOSFET. So these two must be little bit like away from each other, and they should be away from this particular internal circuitry. Okay. Good. Coming back to the ground wiring. So ground wiring, as you can see, we have these ground wirings blue colors. Okay, so or here it is shown in red color also. Okay, so these must be little bit thicker lines. Okay, that's the main understanding that they are telling, because which these have large current flow, like each of the lines actually having very high current that is flowing. So that's the reason. In addition, they have to have little bit thicker lines. Okay. And one more thing that you can see is the pull the wiring thick and short. That's the main like concept that we have to use. So all these blue wires or red wires, we have to have little bit thick lines as well as short line, very short. Okay, small lines. Okay, as you can see, the blue line is ground line if of the IC. So blue line is near the ICs, and make the ground of the IC and the ground of the peripheral parts common. So it means this is the ground of the IC, blue lines, and this is the ground of the outputs that you are seeing. So they have to have a very common line. They should not be very different line. Yes, you should not make a cut here and then later you connect it. No, not needed. Okay, you make a common line. Okay, that's the main understanding. Coming back to the more attention like about the large current. So large current, as you can see, whichever is connected like marked red, they are the ones which are carrying the large current, that is high current. And these what you have to do is you must wire it short and thick. That's the main understanding we should have during the board layout design. So these lines which is marked in red must be little thicker, as well as very small line, that is short line. And high impedance line near the red lines, because it has large noises, so it will be having it must have high impedance also. Okay, sorry, it should not have placed near high impedance line. Do not place the IC and high impedance line near the red lines, because it has large current. Okay, or large noise also, because it is working with very like AC sources directly. So hope you have a very good understanding about this particular PFC correction IC that we have just now seen. And if you do have any question regarding the design and details of this particular power factor correction controller IC that we have just now discussed, and if you are going to utilize either this IC or any other power factor correction IC for your any application like refrigerators or washing machines, or AC DC adapters, or you have LED drivers. So LED drivers are requiring these days a lot power factor correction. Okay, so that's the main understanding, and AC adapters are also there. So those things are actually utilizing power factor correction IC. So you should be able to now in a position to extend the same concept that I have made you understand, like how to read the particular data sheet, what are the important parameters that we need to take care into account. So those things we can always utilize from any of the particular power factor correction IC that you want to see and that you want to utilize in your particular projects. So thank you so much guys. Bye.